All right, Loren, teach us about system design on easy mode.
Hi, folks. I'm Loren. I came here from Brooklyn, where we don't have scooters everywhere. It's so nice in Austin that anywhere I go, I can take a scooter and go around, and it's such a nice, easy way to move my body around. So thank you, Austin, for having scooters, allowing them on your streets. Thank you to Mason and the PyTexas team for having me. Thank you all for your attention. I'm happy to be here to share about something called durable execution and how it substantially simplifies a wide range of system design problems. So I'm Loren. I'm a consultant and open source maintainer. Previously, I worked on Temporal's JavaScript runtime and wrote a book on GraphQL with John Ressig called The GraphQL Guide. Today, I'll start out by defining what durable execution is, talk about some new possibilities for how you can code that it opens up, talk a little bit about how it works, and then go through some system design patterns. And I won't assume knowledge of any of them, so I'll try to give a concise summary of what it is before I talk about how durable execution either obviates it, makes it unnecessary, or makes it easy to do. So what the heck is this thing called durable execution? So an important property of normal execution is that functions fail to complete executing in a number of different situations. For instance, the process crashes, maybe a divided by zero or unhandled exception. Maybe the process is killed by the OS, or the pod is killed by the Kubernetes node because it used too much CPU or RAM. The machine could lose power. I might deploy new code, and usually I have a graceful shutdown period for the old code to finish running before I switch over to the new. But maybe I'm doing something that takes a long time, and I'm still running by the time I get the sig kill at the end of the shutdown window. So then there's lots of transient failures that could happen. Let's say in downstream dependencies, maybe the database I'm talking to it can't reach at the moment, or some downstream service or third-party API, and maybe I need to retry that. And if I take a long time retrying, then maybe I'll get cut off when I get a new code deploy. So it's more likely the longer I take that won't be able to finish. And then, or if I don't handle the failure, then I might have a crashed process. So in durable execution, functions are guaranteed to complete executing. So if I have this process order function with 3 steps: reserve from the inventory service, and then charge some payment, and then send a package. If the first 2 steps run successfully, and then the process running this function dies, I'm guaranteed that this function will continue running on line 4 in a different process. So I have a guarantee that no matter what happens to the process running this, it will continue running and complete. And then when it continues running on the new process, all of the state, like what's happened previously and local variables, call stack threads, everything is intact. Also in durable execution, transient failures are automatically retried. So let's say in the charge step, I'm trying to talk to the Stripe API and it's temporarily down, then it'll automatically be timed out and retried. By default, exponential will back off forever. And then whenever that completes, that charge step, maybe it took minutes or days, whenever that completes, you'll reliably run the next line 4 and send the package. So durable execution is coding at a higher level of abstraction, sort of like in high-level language like Python. You don't have to worry about memory management like you do in a low-level language like C. Durable code is a higher level of abstraction than normal code. You don't have to be concerned about the infrastructure that the code is running on, or the availability of anything downstream that you depend on. Because everything that you depend on, if it's not reachable now, it'll automatically be retried until it is reachable. So there are a lot of ways in which we code that is predicated on the fact that what we're working with is this primitive of a normal volatile function that might die anytime. So we don't trust functions. We don't trust that some set of statements will complete. We only trust things that we've stored to disk, that we persisted, probably replicated on multiple disks. And that has a big effect on how we write code. And when you have the primitive of a durable function, it changes a lot about how you write code. And it opens up some new possibilities, one of which is you can sleep for an arbitrary period of time. So here we're sleeping for 1 month. And normally you can't do that because you don't have confidence that your process will be around in 1 month, and you don't want to take up resources for that time. Let's say 1 thread per sleep. I'm going to run out of threads. And in durable code, you can write this in a production function, and it will work fine. You're guaranteed that this sleep will resolve in 1 month, and that you'll go to the next line of code. And You also don't need to take up resources during that time, except for like a timer entry in a database. The system will automatically unload this code, and whenever that timer goes off in the DB, it'll rebuild the state of the function and continue running. Once I have these functions in production that are running for very long periods of time, I might want to be able to send them RPCs. I might want to tell them like, hey, do something different or do something new now. And I might want to get their state, like, hey, what's your current state of your function? So you can send RPCs to durable code executions. They can also run forever. So this, I don't need to like return at the end of the function. I could wait for an RPC to come, or I can wait for this sleep to happen in a loop, like I'm modeling a subscription, and I sleep for 1 month in a loop and charge the user every month for the lifetime of the user. So it lasts like indefinitely. I also don't have to use a database in many cases, because I can like send information to this function and get information out of it. And the function can like, in Python, it's modeled as an annotated class, and each function execution is like a instance of a class with a run method. And other methods for each RPC handler. So you might like save some state in the run method in an instance variable, and then access it, change it in the RPC handler methods. So you could have some data that you return from like a get current state RPC, and not have to use the database. You're just storing it in a local variable or instance variable, and you don't need to store it in the database. And you're guaranteed that for the life of this function, and even afterward, that value will be correct. Correct based on, like, always be there and always exist, and always be correct based on whatever has happened to that function previously, like whatever the arguments were when you started or whatever RPCs you sent since then. So in summary, durable execution is process independent with automatic retries and timeouts. Sleep for arbitrary periods of time, send it RPCs, have functions that run forever, and you can use local variables or instance variables instead of a database. But how the heck does this work? So here's a system diagram of temporal, which is the one I'm most familiar with and where I used to work. There are a number of different durable execution systems, and most of them have a similar diagram. On the left side, we have application developers, so us writing our application code. And on the right, we have a platform team that hosts the open source temporal service cluster of Go services and databases. And each part of this is MIT licensed open source. And the temporal service side takes care of the durability for you. So if I want to start a durable function, I'll use the client library in the top left, somewhere in my application. I've got a new user subscribing. I want to start a subscription function. You connect to the service, and you say, okay, I want to start this thing. The service adds it to a queue, and there's workers that you have pulling on the queue. They pick up, okay, I need to, and then the workers have your durable code. So they pick up this task, okay, I need to run the subscription function. Here's the arguments, like the user and the payment method, and it will run that code. And any step that it takes, like a sleep or other things, it reports back to the service what happened. So the service adds it to the log of every thing that has happened to this function, or anything this function has done. And whenever new things happen, like a sleep timer goes off, or you get an RPC from a client, it gets added to a queue. The worker picks it up and continues running. So for instance, if it gets a RPC, it'll run that method handler. So here's a family tree of some of the main durable execution systems. It was invented at Amazon, so they were one of the early adopters of microservices. They realized that, okay, I can't call synchronously between microservices reliably in production, so they went to event-driven architecture, communicating asynchronously through queues, and they were like, oh crap, that gets really complicated really fast, and they developed something called Simple Workflow Service, which is AWS SWF, which was the first version of durable code and a much nicer way of communicating between services. Azure Durable Functions has a similar durable execution service. Cadence is used by Uber to communicate across over 1,000 of their microservices, and Cadence was forked in 2019 to become Temporal, which is now a company with over 200 people working on improving it. It's used by a ton of companies, including Stripe, HashiCorp, Netflix. Every Snap story is a durable function. Every Airbnb booking, Coinbase transaction. So the last section, system design patterns. We have 10 minutes. Let's see. So I highly recommend microservices.io for listing distributed system patterns, and Byte.go is a great newsletter for system design. Circuit breakers. Let's say I have a service-oriented architecture, and I'm synchronously calling between services. Service A calls me, I'm service B, and I call service C. When I get a request from service A, I need to do something and then call C. And if C is taking a long time to respond, then I might, let's say I have a thread per open request, then I might build up open requests or threads until I have some resource exhausted, like number of threads, and then I'm going to stop responding to requests from service A. So then A will get backed up and resource exhausted, and you can have a cascading failure. So one solution to this is called the circuit breaker pattern. So I'm service B. Instead of directly calling service C, I will have a proxy that forwards usually the request to service C for me, and it'll keep track of how often C is timing out and stop forwarding on request to C. The proxy will immediately return failure to service B, and then like set a timer, and then after a while try doing requests again. So it gives a break on service C, and it gets immediate failures for me in service B. In durable execution, you don't need to do this because like every call that you make is automatically retried for you with exponential backoff. Event-driven architecture. So we saw one of the problems with synchronously calling between services. So a common solution to this is to have them communicate asynchronously by a message bus. And that's event-driven architecture. Here's an example. A client on the top left creates an order. You post to /orders. You have the API server that writes order created event to the message bus. And then there's a payment service that listens, consumes that event, order created event, does something, sends the order paid event to the bus. Fulfillment service listens to that event, does the fulfillment, and sends order fulfilled to the bus. And there's other services like the analytics service that consumes all of them. A great part of this, a great aspect of this is that it's very decoupled at runtime. So in this scenario, the fulfillment service can go down, and the payment service can continue running. In the synchronous case of like service B, it's not finished until it successfully calls service C. So it's like depending on service C being up and running. Here, it's not depending. Payment service can continue doing its work and publishing order paid events to the bus, even if the fulfillment service is down and not consuming them. And the fulfillment service isn't missing work, because when it comes back up, it can go through the backlog of order paid events. So in durable execution, you also have decoupled runtime. You don't need any particular step or downstream service or dependency to be up at the time, because you'll have retries with exponential backoff that'll eventually get this to work. And so you have decoupled runtime, but you also have much better developer experience at design time when you're building. So an issue with EDA at design time is that it's not decoupled. It's like tightly coupled. You have to like make changes in lockstep. So if I'm the API server and I want to change my order created event to like a order submitted event, or make some breaking changes to the data format, then I have to figure out all of the other teams in my company that are depending on this event and ask them to update their code and push it to production, and then I can make my change. You have to do things in lockstep, and it's also hard to understand what's happening in the system. Like here, there's only one business process, and I laid it out like sequentially for you. But in reality, in production, you're going to have lots of services, lots of different events that are hard to observe. Like hopefully you have distributed tracing set up, and you can see, but sort of like the behavior is emergent and complex, and can be hard to understand. Versus in the durable execution land, you can look at a business process logic in code and read and see what it does. And you also have a log in of every production function execution, so you can see what each function does and every step that it took, or currently running functions, what step they're currently on. So it's much easier to grok and understand and edit your code, see like change what steps happen when, and redeploy. So easier to change, understand, evolve, and work with than EDA. Sagas. Let's see, 15 minutes, okay, great. Sagas are long-running transactions. They are when I have some data that I need to update, and the data isn't in like a single partition of a single database. So I can't use a transaction, like a database level transaction to update it. I need to split up these state updates into multiple steps. And if any discrete step fails, then I undo all the previous steps that happened, what are called compensating actions. Compensate for this failure by undoing each of the previous steps. So it's a type of transaction that isn't atomic and doesn't hold locks and is eventually consistent. So it's a way of updating data that's across multiple databases or services. And the main two ways of implementing Sagas are with choreography and orchestration. Choreography is the event-driven architecture way where you're writing messages to a bus. Orchestration is like a central orchestrator that has the logic of like what the steps are, and it takes care of scheduling, executing, and retrying each of the steps. Chris Richardson in the book Microservice Patterns recommends using orchestration for all but the simplest of Sagas because of how complex it can get, choreography can get, as we talked about earlier in the event-driven architecture section. So recommends using orchestration, and the problem with orchestration is that traditional orchestration is that you are defining logic in a DSL, like a YAML file or a JSON file. You have to like this step and this step, like if, thens, and loops are all done in like JSON, and that's not nice to work with. It's hard to write and read and debug and run, and it's much better to when you're defining logic to define logic in code, because you have the full expressivity of a Turing complete language, and you can use your normal software development lifecycle. You can run it locally. You can debug it locally. So much nicer DX to use code than a DSL, and durable code is basically like automatically orchestrated for you. Each step is scheduled and retried for you. So you can think of durable code as code-based automatic orchestration. And it's a great way to do Sagas. So we have this process order function process from before with 3 steps. If we want to make this into a Saga, then we need to add compensating actions. We need to catch any failures and undo previous steps. So we try and catch. Let's say the reserve step on line 2 succeeds, and then chard succeeds, and then we get to send package, and it has a failure. And it's not like an intermittent retriable failure. It's some application level non-retriable failure, like USPS returned, like address doesn't exist. So this isn't going to work through retrying. So instead of continuing to retry, it throws. I catch it. On line 9, I refund, so I undo the charge step, and then I raise, and then I catch, and then I unreserve the inventory that I reserved in line 2. So if this is a durable function, this is a accurate, complete transaction, or accurate Saga. If this is a normal function, then it's not, because it's not correct, because I could say the process could die after line 7, and then I never refund the user and never unreserve the inventory. So Saga is really easy to implement when you have a durable function. Transactional outboxes. Okay. So if I'm doing EDA, oftentimes if I'm a service and I get an event, I make some state update to my local state in my database, and then after that I submit another message to the bus. The issue is that if after I do my local state update, I crash, then I'm going to fail to write the message to the bus. And everything after me that depends on that message won't happen. So my system will be like an incomplete or inconsistent state. For example, if I'm the payment service, I write my payment record, successful payment record to my DB, and then I crash before I send the order paid event. Then fulfillment service won't know to fulfill. So I'll have a user without a package but having been paid. And a solution to this is called a transactional outbox or transfer queue. So in the payment service, in a transaction, when I update my local state, like adding a payment record, in the transaction in the same partition, I'm going to add the event that I want eventually to get to the bus in a sort of mini queue. In that for each partition has its own mini queue. And then I have some separate process that goes through all of the transfer queues in each of the partitions in my data store and reads them and sends them to the bus. And if it successfully sends to the bus, then it takes it off that transfer queue. And you have deduplication and retries on failure. So assuming you implemented that correctly, then you have this guarantee that because it's in a transaction and because it eventually gets sent to the bus, that you have like this eventually consistent thing. So that's transfer queue or transactional outbox, and you don't need to do it in durable code because the entire pattern is predicated on the fact that I don't know when I have multiple steps that all of the steps will complete running. So thank you a lot. When I have a durable function and I have one step is write to my local database and the next step is publish to the bus, then that next step is guaranteed to happen. So I don't need a transactional outbox. Event sourcing. So this is a way of like storing state. On the top, we have the normal way without event sourcing. This isn't 3 rows. This is a single row in 3 different states. So I insert a row with order ID 1001, quantity 5, and then I update the quantity to 6, and then I update the state to paid. And so I'm left with 1 row with quantity 6 and state paid. With event sourcing, instead of doing these updates, I am appending events to an immutable log, and each event is like what happened. So a new order row is the event ID 2001, and then I modify order event, and then an order payment event. So a downside to that is in order to know the state of this order, I can't look at the last event because it doesn't have the quantity. I have to like read through all the past events for a certain domain model. So you usually have some other view, like a read view or materialized view, where you're reading the current state of the world. But some benefits that event sourcing gets you is that you have a complete visibility or audit log of what happened to this business object in the past. And you can also replay to any point in time to see what the state of the world was. And most durable execution systems are implemented with event sourcing under the hood. So each production function execution has this event log, and so you can see what happened. And you can also you have some bug that's hard to diagnose in production. You can download that event log and run it locally against your code, and replay your code to see what happened and run it in a debugger. So you get great visibility and great debuggability with this sort of like automatically event-sourced function execution. CQRS we'll skip in the interest of time, separating the commands of the writes from the queries. Depending on which level you're applying this to durable code, either it's unnecessary or it's done for you. Distributed cron jobs, let's say I want something to happen periodically. I can have a cron tab on a Linux machine in production. The issues with that are it depends on this one machine being up and has limited throughput. So if I want something to be reliable and scalable, then I want some distributed cron solution. And durable execution is a great fit for this because it scales horizontally in the number of executions. So I can have billions of executions, and all of them could be sleeping for arbitrary periods of time. So waking up whenever I want them to run the next job. Task queues. So there was a article from last year that was voted up on Hacker News called "Too Many Problems with the Many Problems with Celery," and one of them was Celery prefetches jobs, so it gets 4 at a time, and if the first one takes a day, the next 3 are delayed, even if they're take a few minutes, because it's working on 1 at a time and gets 4. In durable execution, you have many slots in parallel that a worker can be running, like many function executions that can be doing, and it only fetches 1 at a time. So it's much better in this scenario. Celery loses jobs by default. So if a task raises an exception or a worker process dies, then you lose that task. In durable execution, you don't. Whenever there's a failure, it'll automatically get timed out and rescheduled. Celery retry defaults are bad. So they recommend doing exponential backoff, which is what durable execution does by default. no transactional job in queuing. So talking about the transactional outbox pattern, and author says like, don't use celery if you need this because you can't. You don't need it with durable code. Canvas, chords, and friends encourage brittle pipelines. So if you have some pipeline of multiple jobs that you need to happen together, like in a chain, the author says it's a recipe for losing jobs or having broken workflows because celery doesn't have transactional job in queuing. So you could have like the first step in a chain happen, but the rest won't happen in various error states. So it's like they're like, don't use celery for this. You don't use these APIs. Versus if in durable code, if you have a function with multiple steps, you're guaranteed that they will all complete. Another complaint was that the API isn't Pythonic. And I don't know about all durable execution systems, but for temporal, the Python runtime is very Pythonic. Talk to Chad, who built it, who's at the temporal booth today. State machines. So a common pattern is I have some business process that has multiple states that it's in, and I want it to be done reliably. So I split this process into multiple steps that I put on job queues, and I update the current state of this process after every step. And that can be a lot of work, a lot of code to write, like in queuing and polling and updating a database. And I guess it's a lot of code to write and to get correct, versus in durable code, you don't need to do all that plumbing work of talking to the database or talking to a queue. You can structure your code if you want as a state machine, but you don't need to be talking yourself to a database. So to recap, we defined what durable execution is, talked about some new possibilities for how to program that it opens up, a little bit about how it works, and then some distributed system patterns and how temporal either makes them unnecessary or easier. So we had circuit breakers, don't need to do, event-driven architecture, same decoupled at runtime, better DX, Sagas, really easy to do, transactional outboxes, don't need to do, event sourcing, done for you automatically, CQRS, partially don't need, partially done for you, distributed cron jobs, really easy to do, task queues, automatically done for you in a better way than Celery's defaults, and state machines, easy to do. And temporal.io for more info. I'm at Loren Sands-Ramshaw on Twitter if you have any questions. Also, Loren@GraphQL.guide is my email. I'm a consultant with Bandwidth, so if you have any, if you'd like any help building your thing, I'd be happy to take a look and see if I can help. And those are the slides.
Awesome. I've got a couple of questions for you here that have been coming through. And by the way, Loren is also on the Discord, so you can chat with him there as well. Okay, first off, how can you tell if a failure is transient or non-transient? What's your criteria there?
Sure. So I guess each step is like a normal Python function, and if you let something throw, it's treated as a retriable error. If you catch something, then you can throw a non-retriable error, failure. So it's a class that you import from the library to indicate that whatever happened is not retriable. Don't try to reschedule this.
Okay. Can you talk about the data persistence layer and any concerns around PCI, PII, GDPR rights, and any of those things that need to be considered?
So I guess like there's a number of different options for a persistence layer for temporal at least. Like I don't know about some of the hosted services like AWS, SWF, or Azure Durable Functions, like whether they're PCI compliant or what database they use. But for temporal, you can use MySQL or Postgres or Cassandra. Usually Cassandra for higher write throughput and scale. And I mean, if you want to go through PCI and GDPR in that open source cluster that you host, you can do that.
Wander over this way with me. How do durable execution workers know what function to pick up and in what order?
Sorry, say it again?
How do durable execution workers know what function to pick up and in what order? How do they keep track of the state of what needs to be?
So the workers don't need to keep up much state. The cluster, the service is taking care of when to add things to the queue, and the first, and like all the workers are polling whenever they have like an open slot. Like I can do 100 executions in parallel. If I have one of those open, I will poll, and whichever the first one that gets a new task on the queue, we'll get that.
We'll help take care of that.
Yeah.
Okay. How does the durable execution handle it if the code has changed while the function was suspended?
Sure. So if you are changing the code of a execution running in production, there are a couple of different ways to do it. You can so if the code, if the execution has hasn't gotten to this point of code, then you can just update it. If it's already gone through it, then you can't update it, because the way the system is implemented is that it has to, in order to rebuild the state of a function, it has to replay all previous events. And if you try to replay the event log on different code, it'll not work. So there's a couple different ways you can solve this. One is you can deploy a separate worker that only takes the new version of the code that only takes new production function executions. So all the existing ones will run in the old code, and then whenever those are done, you can retire the old code. Another way is to like have an if-then statement, depending on what, like if version is 1, do this logic, otherwise do some other logic.
Okay. How do you see durable execution affecting game development?
Game development. So I guess like for the trade-off for durable execution is that you are writing to disk a lot. You have higher latency than if you weren't persisting anything. So there are certain things like for real-time gaming where you wouldn't want to use it. But for anything where you can wait like 20 milliseconds, like, I don't know, the information about the user account, yeah, anything in non-real time you could use a durable function for in gaming.
I think that also helps answer the question, is durable execution used in real-time critical systems like air and spacecraft and their support systems? And if not, why not? I would guess that the high latency would probably make them not well-suited for that.
Yeah, I mean, it depends on how you think of as high latency. Like tens of milliseconds is fine, but if you're trying to do like single-digit milliseconds, then it'd be hard.
Right. All right, I'll do one more here. How can I trust that the durable execution workers are not malfunctioning?
How can you trust the workers are not malfunctioning? I guess the system...
The workers.
Pardon?
Who watches the workers?
It's fine for, like, the system designed to like not trust workers, to only trust what's in the database. So if like a worker dies, the everything that the worker does, every task that it picks up has like a timeout associated with it. So the server will notice that this task there's no result from this task in a while, so it'll treat it as failed and reschedule it.
I sent this assignment out a little while ago and it never returned. Guess I should dispatch that again. Nice. Okay, well, thank you, Loren.
Sure.
This is fantastic. Thanks, everybody.